Zeal Education Society, redefining excellence.
Hello, good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering, Zeal College of Engineering and Research, Pune. In this video lecture of Electrical Machines 2, we are going to learn the voltage regulation of alternator by EMF method. In a previous video lecture, we have learned the voltage regulation of alternator by direct loading method that is used for small machines. Now in this video lecture, we are going to learn the voltage regulation of alternator by synchronous impedance method, also known as EMF method, also known as Bain-Eisenberg method. What are the data required for this method? That you have to conduct the open circuit test and short circuit test on the alternator. These two tests are required. In addition to that, it is necessary to measure the armature winding resistance. Means that third test is also required. Now let us have an open circuit test. Now here it is the circuit diagram given for the alternator is as shown in the circuit. This one is the stator of the alternator. Means alternator has two main parts, that is the stator and the rotor. The stator generally consists of the armature winding, which is generally a star connected. Now the RYB is the star connected armature winding, and to this armature winding the terminals, these three terminals are taken out, and the triple pole single throw switch is connected here. Now this ammeter which is shown here, that can be connected in R line also, it can be connected here also in series with the line. Then this, when the switch is open, it is open circuit, and when switch is closed, it will become short circuit because the three terminals on the right hand side of the switch are shorted by a thick wire. Okay. Then the voltmeter is connected between the two lines to measure the line voltage. If the neutral is available, you can connect the voltmeter between the any line and neutral. But mostly it is connected between the two lines. Okay. That will read the line voltage, and later on you can convert that voltage into phase voltage. And as the alternator is star connected, whatever the ammeter reading, that will read the line voltage equal to line current equal to phase current. Sorry. Then turn to the rotor. On the rotor, generally the field winding is placed. The F1, F2 is the field winding, and which is excited by DC source. The DC source is here. It may be a rectifier, or one can use the another things in the laboratory. Then this is the double pole single throw switch. The variable rheostat is connected in series with the field winding in order to vary the field current. One may use the potential divider also. This rheostat as a potential divider in order to vary the field current. As the DC source is used to excite the field winding, the ammeter used must be as per the polarity, must be connected as per the correct polarity. That is, the positive and negative must be shown, and the instrument means the permanent magnet moving coil ammeter must be used. Generally the field current is very small, 1 to 2 ampere is sufficient for the laboratory experiment, the range of this ammeter. And the range of the voltmeter connected in the armature winding depends on the armature loading or the rated voltage of the alternator. Say if it is 415 volts, say, or 400 volt, you have to connect the voltmeter of 500 volt, because the range, standard ranges available are 0 to 500 or 0 to 600 volt, and that's why we must use it 0 to say 600 volt. Now here ammeter, say it is a 3 kV alternator and the current is rated current is 4.2 ampere. Therefore the standard range of the meter is 0 to 5 ampere. So you can use the range 0 to 5 ampere here, and both these instruments connected in the armature circuit must be permanent magnet, the moving iron type, that is used for the AC, moving iron type. So in this way we have seen the connection on the stator side as well on the rotor side. Now let us turn to the prime mover. Prime mover generally used in the laboratory is the DC shunt motor, which can be adjusted to any desired speed or required speed. Now see, go to the procedure. First thing is, keep this switch open in order to conduct the open circuit test, that is also known as no load test, because no flow of current because of the switch is open or no load is connected. Then rotate the alternator by prime mover at a synchronous speed given by ns equal to 120 f upon p. Okay. Then the next. Now see, the alternator which we have connected, assumed, say the alternator is 3 phase 3 kVA, 4 pole, 415 volt. This is the rated voltage, that is the voltage between the lines, that is line voltage. Unless stated otherwise, given values are always line values. This 4.2 ampere is also a line value, that is a line current. And that's why in order to measure this current, we must use the ammeter 0 to 5 ampere, or if you want to measure higher value, you can use the 0 to 10 ampere, that is the standard range available, or the standard range may be a 0 to 7.5 ampere. Okay. And here also you can use the voltmeter 0 to 600. Okay. So this one. Now switch on the DC excitation to the field winding. Then go on increasing the field current step by step and note down the corresponding voltmeter reading till you will get the rated voltage and 1.5 times the rated terminal voltage. So when you switch on the excitation, the field current will be 0, the induced EMF in the armature will also be 0, or maybe there may be some reading because of the residual magnetism. And if you go on increasing the field current step by step, for every step note down the corresponding voltmeter reading, that is the EMF generated by the alternator. And in this way, go on increasing the field current such a way that you will reach to the, or voltmeter will read 415 in this case, that is the rated voltage. And in this way further go on increasing the field current till you will get the voltmeter reading 1.5 times the rated value. And in this way it completes the open circuit test. Now we have to turn to the short circuit test. Now before starting the short circuit test, keep this rheostat to the 0 position, that is make the excitation, this feed current to 0. This feed current 0, which was earlier increased, earlier test, in OC test, it was increased from 0 to certain value. Now make it to 0 once again and then close this switch. Close this triple pole single throw switch in order to short circuit the armature winding. Okay, this due precaution must be taken. Then further, as it is short circuited, you have to take very cautiously, precaution must be taken while increasing this field current. Okay. Now make the excitation to 0 and then close this HTTP switch. Increase the excitation, increase this field current slowly, very slowly, so that you will get the rated armature current, that is 4.2 ampere in this case. And the next reading will be, the first reading, this excitation 0, this current 0, armature current 0. Next excitation, go on increasing the excitation till you will get here 4.2 ampere, that is the rated current. Then further increase the excitation such a way that you will get here reading 1.5 times the rated full load current. In this way, the open circuit test and short circuit test is completed. Now see the observation table. Now in the observation table, see the field current and the generated EMF. As the voltmeter is connected between the lines, it will measure the line value, and later on you have to convert this into per phase, dividing it by √3. Okay, as the field current increases, say 0.1, 0.2, 0.3, note down the corresponding generated EMF reading. And say at 0.5 you are getting the rated voltage, say 415 volt here. We don't know at what field current it will get, but go on increasing the field current such a way that you will get 415 and further go on increasing the field current so that you will get 1.5 times the rated voltage. In this way, the open circuit test readings are completed. Open circuit test is completed. Now short circuit test readings. Keep the excitation which was increased up to this value, go on decreasing to 0. Then close the short circuit test side switch, triple pole switch, make it short circuit and slowly increase the field current, this field current such a way that you will get the rated current, that means here 4.2 ampere in this case, and increase the field current such a way that you will get here 1.5 times the rated current, that means 6.3 ampere in this case. Okay. So this is about the open circuit test and short circuit test readings. Now we have to find out the ZS, that is the synchronous impedance. The formula is open circuit EMF per phase divided by short circuit current per phase. Both obtained at the same field current. This we will obtain while plotting the open circuit test characteristics and short circuit current characteristics, SCC, OCC and SCC. Okay. Now see, measurement of the armature. This is the third test, measurement of the armature winding resistance. Now the armature is generally star connected, and here you can use the fishbone bridge or the digital multimeter, the DMM you can use. Okay, digital multimeter. Between any two terminals of the star connection, you connect the DMM. Now this the third phase is open, and therefore DMM will read the resistance of these two windings, because these two windings are connected in series. So observe here, the alternator is star connected, therefore digital multimeter DMM will read the DC value of the resistance, and that is twice R, twice RA DC equal to R. This is R is the DMM reading, and therefore RA DC, DC resistance of the armature winding is R divided by 2. That is the digital multimeter reading divided by 2. Now considering the skin effect, the AC resistance will be 1.6 times the RDC resistance. Okay. Now similarly, if the alternator winding is delta connected, then you have to connect the DMM between any two terminals. Now this DMM will read the equivalent resistance, that is these two resistances, RA in series, and that is in parallel with RA in this way. So when it is connected in the delta, the DMM reading will be twice RA, means this RA plus this RA, parallel with this RA, and that will read R, and therefore RDC equal to 1.5 times R. Whatever the DMM reading multiplied by 1.5 times, that will be RDC resistance, and considering the skin effect, AC resistance would be 1.6 times the RDC resistance. Okay. Now further, what is the equivalent resistance of the alternator during the open circuit test? During the open circuit test, this one is kept open, and therefore there is no flow of armature current. Armature current is 0. And therefore, see, pay attention, as armature current is 0, the E0 equal to VPH plus IA is ZS, and as IA is equal to 0, E0 equal to VPH. Means whatever the generated voltage in the armature winding, same is available across the terminal of the alternator. Okay, and the next one is the equivalent circuit during the short circuit test. Means these two terminals are shorted here, and this is drawn on a per phase basis, so it is shorted. And what will be this ammeter reading? That is IA equal to ISC. Okay, that is full load current. Now here the equivalent circuit is as the circuit is short circuited, IA equal to ISC, and therefore this E0 or ZS equal to E0 equal to this generated EMF equal to all this voltage generated will drop across this impedance, and therefore E0 equal to ISC into ZS, and therefore synchronous impedance ZS equal to E0 upon ISC, that is open circuit EMF per phase divided by short circuit current per phase, both measured at the same field current. Okay, so this is the OCC and SCC, open circuit characteristics and short circuit characteristics of the alternator. This is the general figure. Now the field current, see, field current is taken on the x-axis. This is the field current, and on y-axis the open circuit EMF per phase, and second y-axis is the short circuit current per phase. Okay, now plot the OCC from the open circuit test. So OCC is the open circuit characteristics. It is also known as no load curve, or also known as magnetization curve. Now initially this curve is a straight line, but later on it becomes a flat. The reason is because of the magnetic saturation of the magnetic material. Now if there is no magnetic saturation, this curve, this OCC would be a straight line like this, that is the air gap line, and it is drawn tangent to the OCC from the origin. Okay, and the short circuit characteristics, that is 0, 0, and there will be a 3 reading only. This is the full load current, this is full load current, and here will be some 1.5 times the full load current. Join this point. The short circuit characteristics are the straight line. It is the straight line passing through the origin as shown. So this is the SCC, short circuit current characteristics, passing through the origin, and it is a straight line. Now how to find out the ZS? Okay. Now ZS, at this field current, say OA is the field current, and at this field current OA, what is the open circuit EMF? Open circuit EMF is AC. Open circuit EMF is AC, and the short circuit current is AB, where AB is the full load current. Means generally the field current is considered in a such a way that it will read the full load current. Short circuit current equal to full load current. So ZS equal to synchronous impedance equal to open circuit EMF per phase divided by short circuit current per phase. It is equal to XS equal to. We have already measured the armature resistance, and once you obtain ZS, you can find out XS, that is a synchronous reactance per phase, where ZS is the synchronous impedance in ohm per phase, and similarly XS is synchronous reactance in ohm per phase. And what is this one? See, ZS. Once you have obtained the synchronous impedance, now you can plot the graph of field current versus the ZS. So it is observed that at a low field current, low values of the field current, the ZS is almost constant. But as the field current increases, because of the saturation, the ZS drops. ZS decreases. Now see, this is the actual curve which we have plotted. We have to plot this OCC, that is the open circuit characteristics, that is the curve between the open circuit EMF per phase on the y-axis to the field current on the y-axis. Field current on the x-axis. Field current on the x-axis. See here, field current on the x-axis. Now we have to find out, and the short circuit characteristics is also drawn. Now the ZS equal to, now how to choose this point? OA is the field current required. OA is the field current required to circulate full load short circuit current. To circulate full load short circuit current, and from this, at this field current OA, what is this open circuit EMF? Open circuit EMF is AC. So ZS equal to AC upon AB, where AB is the full load short circuit current. And in this way, both these AC and AB are obtained at the same field current, that is OA, and generally it is taken at a full load current. Okay, where AB is the short circuit current per phase equal to full load current. AB equal to short circuit current per phase, and that is equal to full load current, and ZS is generally obtained from the full load current short circuit test. So here also we have obtained the ZS synchronous impedance. We have already tested for the armature winding resistance. You can find out now the synchronous reactance XS equal to square root of ZS square, ZS square minus RA square. Here should be minus sign, here it is by mistake. It is so here it is. So synchronous reactance XS equal to square root of ZS square minus RA square. So in this way we have obtained the synchronous impedance per phase, then the armature winding resistance and armature winding synchronous reactance. So by using these open circuit test and short circuit test characteristics, we have obtained the winding parameters in this video. In the next, we will stop here, and in the next video lecture, we are going to learn how to find the no load EMF, no load voltage, so that we can find out the voltage regulation, and we will study the various types of various phasor diagrams at a lagging power factor, unity power factor, and leading power factor.